about your game, but I'm not the one to sit around and be played. Call me up with no shame. All your words sound the same. Yeah, already know about your game, but I'm not the one to sit around and be played. If you come around just to play me, don't bother, cause you ain't overdue. Don't even try to convince me. Don't bother, cause now I see it through. If you come around just to play me, don't bother, cause you ain't overdue. Don't even try to convince me. Don't bother, cause now I see it through. Every now and then I think what we had was something real. Don't know why, cause I've been hurt like this, but never thought that I would fight for you this much. Don't know why, and tonight I'm not the one to be blamed, cause I ain't the one who hesitates. Yeah, already know about your stupid games. Come around. If you come around just to play me, don't bother, cause you ain't overdue. Don't even try to convince me. Don't bother, cause now I see it through. If you come around just to play me, don't bother, cause you ain't overdue. Don't even try to convince me. Don't bother, cause now I see it through.
Midnight and city lights on the other side. You're calling me up at the same time. I'm in the daylight. You're calling to say hi, but your words they cry. If there's something that you need to say, I know it ain't easy living inside your brain for sure. You keep telling me that it's all okay, but I know, yeah, your silence speaks so loud. Your silence speaks so loud. And I hear you calling out, yeah. We're talking about nothing. Then you said something under your breath. I can't take it, I know what you're thinking. I wish I could fix this, yeah. If there's something that you need to say, I know it ain't easy living inside your brain for sure. You keep telling me that it's all okay, but I know, yeah, your silence speaks so loud. Silence speaks so loud.
Alrighty, how you guys doing today? It's Tuesday. Happy Tuesday. Think we're back. Right. All right. Hope you guys got your coffee. It's been a long November, and now it's December, but we'll see how it's going. You guys doing all right? I managed to catch a case of COVID while I was in Philadelphia. So I'm home, my daughter's not, and we're going to go back once all this clears up. So that's a mess, but, you know, it's okay. We'll get through it. So got a couple things. We'll talk about recursion this week and plotting next week. And we'll talk about the final project today. And then it'll be due, I don't actually need it right by 6 p.m. I can take it slightly after 6 p.m., like up through 11:59 p.m. or so for that. So we'll talk about what the final project's going to be. It's going to use some plotting that we're going to talk about next week, but you can do all the other portions of it without doing the plotting yet. So don't worry too much about that. Yeah. And cool. So we can go from there. Do you guys want to talk about recursion first or the final project first? I'm up for either. And then hopefully the labs are going well. No, you guys aren't asking lots of questions about labs, so I take that as a good sign, I think, but, you know, that's okay. Do let me know if you have questions about the labs. I'm happy to help with those. And if you run a little late on, that's okay. Would rather you get the practice in than just not turn in anything, for sure. So, you know, if you are working on it, great, we can do that. All right, well, let's talk about recursion first then. So let me start up a new project. That's chapter 14, right? Yeah, chapter 14. 14, recursion. And recursion is pretty cool. It's just a fancy way of saying something that calls itself. So I'll show you a quick example. I don't need any of this nonsense. All right, so if we define a method like countdown, it's a real easy, simple one. And countdown has some number. What we're going to do is we're going to print the number. And then we're going to check if the number is greater than 0, we're going to call countdown again. But this time we're going to take number minus 1. So it's recursive in that it is calling itself. So a function calls itself. And it's going to keep on going until it gets to no longer greater than 0, and it will stop. Right? So we can call countdown and say give it 10, and we'll get a nice little countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 when we run it. Now that's not very impressive because we could already do, you know, a count from 10 to 0 without this silly recursion thing. But this is just a simple example showing you, hey, here's a function, the function calls itself. Now you'll notice there's two things here. The first thing, hopefully you'll notice, is that it's designed so that it doesn't run forever. Because if we didn't have this check here and we just called ourselves forever, we would actually crash. And I can show you that real quick. So this is here. It just runs and eventually it crashes. We get the maximum recursion depth exceeded while calling a Python object. And that's just, you know, it means we have done too much recursion, Python is upset and pukes on us. It crashes. Okay, we want to try and avoid that if we can. Another common name for this, they don't call this in Python, but it's a stack overflow in other languages when you run out of room. Hey, Professor Peter and the math crew. Thanks for coming on by. We are actually doing some math here in Python, and we're going to talk about Fibonacci next, if I can, you know, have you interested at least, because I know you guys know what Fibonacci is. All right. So this is our basic example here. Again, in other languages, it's a stack overflow where you just run out of recursion room. Oh, definitely Python. Definitely Python. C++ is terrible. It's just a terrible language. You know, it's not. It's very powerful, but it lets you shoot yourself in the foot. So All right. So our countdown function is recursive. It has the complex case in which we're going to do something. So if it's a complex problem, we're just going to do something. Then what we're going to do is we're going to make the problem simpler, and we're going to approach what we call the base case. So the base case is the problem is solved. It's done. That's as simple as it gets. So if I get to the base case where I'm not greater than 0, that means I'm 0 or less, I'm done. Problem solved. You can't count down any. We're just going to pretend negative numbers don't exist. We're not going to count down any further, right? We stop at 0 because we're sane, right? I mean, negative numbers are really just imaginary anyway. So that's our base case. So you identify a base case, and you find a way to make the problem simpler. Ooh, matrix multiplication to do Fibonacci? You know, in the finite math class I took, we found a non-recursive solution to Fibonacci, and that blew my mind. I was so impressed, because I've always thought Fibonacci was like the coolest sequence, and I didn't know you could do that. But it turns out when you take like the square root of 5 or something like that, you get a really ugly number, and you have to do some rounding, so it's kind of like magic anyway. All right, so if you can find a base case, right, that's the simplest solution, and you're done, you win. Great. It's possible you might be able to solve it with recursion, because you need to be able to know, here's a complex problem. I need to be able to figure out how I can break it down and approach a base case. Then it might be solvable with recursion. And a fun fact, anything solvable with recursion can be solved iteratively, or without recursion, like just a regular loop. It's not always easy, so sometimes recursion is super easy. A golden formula. Oh, the Fibonacci one. So if you guys remember fib, because I never remember how to spell Fibonacci, and if you want like the nth term of Fibonacci, there's like double that. I don't know. I'm terrible at spelling things, so I'm just going to call it fib. Right? If nth is equal to the 0th term, or nth is equal to the first term, you get 1. Right? That's just the rule of Fibonacci. The first 2 terms are 1. Right? Once you've got that, then we can actually calculate the rest of them. If I don't give you back a 1, I can return fib of nth minus 1 plus fib of nth minus 2. Right? That's the mathematical definition for Fibonacci. Right? The previous term plus the previous term. Boom, done. That's it. It might also be worth having in here, so instead of saying we're equal to 0 or equal to 1, let's just say if nth is less than or equal to 1, because if I give you a negative number, I'm just going to pretend you're dumb and give you a 1 anyway, and instead of having to deal with that. It's just a little easier. I mean, we could raise an exception if we wanted to, if you want like the negative 10th Fibonacci term, but I'm just going to give you back 1 because you were dumb for asking. Okay? So that's the easiest, simplest solution for Fibonacci, right? And this will work, right? So we can say for number in range, I don't know, let's start at 0. We can start at 0 and let's go up to, say, 25 maybe. Let's print fib of number. Let's see what we get. Right, so ignore our first little countdown. Here, there we go. So we'll start here. Let's give a nice little print. Let's do that. Let's print fib. There we go. That way we can at least see where it starts. Right. So we start here. But 1, 1, 2 is the sum of the previous 2. Right. 3 is the sum of the previous 2. And you guys know how Fibonacci works, right? 8, 13, 21, 34. So I think this checks out. And just to double check ourselves, let's this should be the 24th term here, right? So we could print number and then like a colon if you wanted, just to make this kind of pretty here. And really, if we want those numbers to line up, we should probably format that, right? We could do a nice formatted string, have number in here with, what is that, a colon with like 2, I don't know, however you do the padding, I forget. All right, it's probably not even worth it now. No. I gotta end that. There we go. So it pads it for us here. Now at least it's gonna line up and look a little prettier. Okay. So the nth here and the value, nth and the value. So the 24th term here. So don't trust me, right? Let's always go, we'll check, Wolfram Alpha is really good at this sort of stuff. We'll go check Wolfram Alpha. I think Bing can even solve some of these, but Wolfram Alpha is just fantastic. So fib of 24, and it knows fib is Fibonacci because Wolfram Alpha is just amazing. 46,368. Uh-oh. Did they not start at 0? Did they not start at 0? Did they not have a 0th term? I always thought I did it wrong when I didn't have a 0th term. Fib of 0. Oh, they start at 0? Okay, they don't start at 1? Alright, I'm just dumb then. So 0 is 0? But then how do you get the first term? Okay. Whatever. We're going to pretend I'm right, and Wolfram Alpha's wrong, because why not? Okay, so this is okay, but now we're going to see, let's crank this up to 40, and let's see what happens. Yeah, no one ever starts Fibonacci with 0, right? It starts with 1, because then you can have this previous sum, and we can have this conversation while it computes. Well, it told me Fibonacci of 0 is 0, right? Or am I not, is it not understanding what I want for, yeah. F of n is the nth Fibonacci number, is 0. I'm going to trust the math profs in chat here and just go with what they say. But you can see this is taking a long time here. This 300, what is that? 14 million, there we go, 24 million, and on and on and on. And what's actually happening here is I am literally adding up the number 1 millions and millions and millions of times here, because this is a stupid solution. It's easy, but it's stupid, because what we're doing is for every Fibonacci number that we ask for here, and this is where it's fun to draw. And I'm just going to show you, I don't even want to go that high here, so let's go up. We'll say fib of 10 becomes fib of 9 plus fib of 8. 8. And 9 becomes 8 and 7. 8 becomes 7 and 6. 7 becomes 6 and 5. And the 8 over here becomes its own 7 and 6. This 7 becomes a 6 and a 5. And this becomes a 5 and a 4. And hopefully you see a problem happening here, right? All of these are branching off into further recursive calls. And every one of those recursive calls, right, needs to be 4 and 3. And then one of those, oh, it moved my 3. That's fine, 4 and 3, and then 3 and 2. 2 actually, we can't even do 2, right? Because 2 becomes 1 and 0. 3 becomes 2 and 1. 2 becomes 1 and 0. So we break all of these down into 1s. And eventually, I can solve the 1s, and I can add up the 1s. Right? And I'll just add up all the 1s millions of times to get to those big numbers, because it's a dumb solution. It's easy, but it's dumb. So, and thankfully, we don't run into that stack overflow problem or the maximum recursion depth, because it does them in order. So the first fib here, when I was trying like fib 36, would call fib 35. The first thing fib 35 would do is call 34. 34 would call 33, 32, 31, 30, 19, on and on and on and on and down. So we don't get tons and tons of them in there, because we're not doing, fib of 1,000. If we did, we would probably overflow. But it's just really slow. So it's a bad solution. So I'm actually going to rename this one here. So refactor rename, right? Don't do more work than you need to. We're going to call this one BadFIB. Okay, and yes, do the refactor, please. So that's BadFIB. Okay, a better fib here. Define better fib takes an nth. And remember, we need to find those two things. We need to know what the base case is, and we need to know how to approach the base case. Right? Well, still, if it's nth of 1 or less, that's the base case. Right? We're done. We know that one. Otherwise, now here we're going to do a little trick. We're going to cheat, because in order to make this faster, I need to be tracking these previous numbers. So what I want to do is I want a helper method here called BetterFib. And BetterFib takes a couple things. It takes the current nth, it takes the previous, and the current value. Or current and previous, I forget, whichever order we want, current and previous. Now, the reason this one is a private helper method is for you to get the nth Fibonacci term, you shouldn't have to tell me the current and the previous values. Right? You shouldn't need any of that. So I'm only going to use it in the public facing method here. And I'll say return BadFIB of, well, it's still the same nth. My current nth is going to be 3, because, or let's go with 2, right? Because 0 and 1 were 1. And then at 2 now, my previous current value is 1 and my previous value is 1. Okay? So I'm going to call a different method. So this one's not actually recursive here. The BadFIB that's private is going to be the recursive one. And in here, we're going to say if nth is equal to the current nth, we're going to return current plus previous, right? So if I want the second Fibonacci number, it's not 0, it's not 1, well, I'm going to call BadFIB. I'm going to say, okay, I want the second. I'm currently at the second. The current was 1, the previous was 1. I'm going to give you back 1 plus 1 is 2. Done. If I don't return it, so this is my new base case now with this better Fibonacci recursive solution. This is the base case when nth is the current nth because I've added up to it. And adding up is going to be way, way, way faster than counting down, right, to 1 and adding up a bunch of 1s. So otherwise, I'm going to return BadFIB of nth, current nth plus 1. And now current is now going to be my current plus the previous. And my previous is now what the current is, right? So add those two together, and then the current is now the previous. And this will recurse until I hit the nth that I want. Now what's cool with this one, if I do BadFIB of the number, we'll watch it. Now this one will go really fast. Yeah, it's done already. Like, we can add up 39 numbers really quick in Python, right? We're not adding up a billion ones here to get this number. We're just adding up 39 numbers. And each time we can, so if we put a breakpoint in here in BadFIB, we can watch this in debug mode. It's really fun. You can watch it show up on the call stack here. Let's see. We're getting there. There it goes. So here's my stack, right, over here on the left. BadFIB at 23, and then BadFIB the private helper at 16. And you see it's tracking the values at each time. So recursion is technically expensive in the fact that every time you call the function, it needs to keep another set of all these arguments and anything we've declared inside the function. It keeps another set in memory, which is okay. It's not the worst thing in the world. So I'm going to keep on stepping into my code. Right, and we'll just keep going here. Let's see how far we can get. We got to get a couple in. Okay, let's see. There we go. So now this is looking for an nth of 7. We're currently at 5. So my current is 5. My previous is 3. Right, we're going to keep on going. So we're going to recurse again. So notice at each one of these, which is really cool in PyCharm, I can see the values at every step of the way, which is really cool. Sorry, it's a little small. I'm not able to zoom that in. But we can see what the values are as we go, which is really cool. So eventually we'll hit 7. Then we're going to return, right? 13 plus 8. Right? We return our value. We're done. And now, you know, we're in the loop, so we're looping again. Here we're doing the next value. Now we're nth is 8, and on and on and on. Okay, so we can see all of that working, which is really cool. So that's a better recursive solution to Fibonacci. And now, you know, obviously you can do this iteratively. Define fib iteratively, right? You don't need recursion to solve it. Just sometimes it just makes life a little easier. But you know, with Fibonacci, it's not so bad, right? So again, we can still say here, and then we can have a current nth equals 2, and while current nth does not equal nth, well, I need a previous, and I need current is 1. So I have next equals current plus previous, and then I have previous equals current, and then I have current equal next, and then my current nth goes up by 1, and then eventually I return current. Right, so we just keep on adding up here until we reach our value, and then we can return what our value is. I think that one gives us the same result. I'm either off by 1 or, we'll see. So let's just print them both. Why not? Number. Let's see what we get. See if I'm off by 1. Yeah, I'm off by 1. So return current plus previous. There we go. That should match. There we go. Cool. Those look good. So again, all we're doing with this while loop is we're using recursion instead of a loop. So that's the easy way. So if the recursion is just a loop here, then it's really easy to replace it with an iterative solution. There are problems that are solvable with recursion that are not just easy loops, though, which makes recursion so much easier to do. And there's a really cool thing I can show you here. This is the Tower of Hanoi visualized. And there's some good ones here. Let's see. I gotta find the right one. I think this one's pretty good. Liang writes a pretty good book. Excuse me. So the idea with this Towers of Hanoi is you want to move all of the disks from one peg to another peg. So we're moving all the disks from A to B. But the problem is you can't put a bigger disk on top of a smaller disk. Otherwise it gets crushed and broken and whatever. That's the problem. So what we do is we solve this recursively, because it's hard to move 5 disks, right? That's a complex problem. What's easier to do is to move less disks. So instead of moving 5 disks from A to B, what I'm going to do is I'm going to move 4 disks from A to C, and then I'll move the 5th disk from A to B, and then I'll move the 4 disks from C back to B. Right? Let me get out my pencil here. So imagine the tower with the disks here, right? 1, 2, 3. We'll just do 3 disks, right? It's hard to move 3, but what I can do is I can move 2 disks to here, 1, 2, take them off of here, move the 3rd disk here, and move those 2 back on top, right? And you're probably thinking to yourself, oh, well, actually, it's kind of hard to move 2 disks, right? Well, sure, okay. So instead of moving 2 disks, let's move 1 disk. So I can move 1 disk from here to here, then I can move the 2nd disk from here to here, and then I can move the 1 disk back on top of it. Right? So do you see, we can approach a base case, which is moving 1 disk is really easy. Moving n disks is just the same as moving n minus 1, moving the nth disk, moving the n minus 1 again. And we just repeat the process. So that probably doesn't make a lot of sense, but if you watch the animation here, it's beautiful. So we're going to move 1, move the 2nd one, move the 1 back on top. So instead of moving 5, we moved 2. And now we're going to move the 3rd, which is moving the 3rd disk and moving the 2 again. Then after we've moved 3, now we're going to move the 4th disk, right, from A to C, and then we'll move the 3 from B back on top of the 4th disk on C. But moving 3 is hard, so I'm going to move 2. Moving 2 is hard, so I'll move 1. Okay, move 1. Now I can move 2. Right, so it's the same idea with this recursive solution. And if you just Google Python Tower of Hanoi, there is a solution for it somewhere. They only got 2 stars, so let's not go with that. How about tutorials point? Let's see if that's any good. Yeah, here we go. This is it, right? If you want to move n from and to with your spare, if n is 1, we're done. That's our base case. If not, we're going to approach the base case by moving n minus 1, and we're going to flip the from. It stays the same. We're going to flip the storage rod and the to, the actual destination. So move n minus 1, right? Then move n, then move n minus 1 again, back on top, right? So to solve it here, you move disk 1, move disk 2, 1, right? The whole thing on and on and on as you go. And that's it. So this is super simple with recursion. This is much harder to do without recursion. And look at that, we're almost done now. We're moving the 5th disk, so now we're moving 4, and on and on and on. Okay? So that's the Towers of Hanoi solution. It's really good. And that's a real common example for using recursion. Okay? So we're actually going to do more with recursion next semester. And unfortunately, you guys are stuck with me next semester. unless they decide to get rid of me, which is, there's always a chance. So the student evals, I think, were finally released today, and like every time you log into Canvas, it's going to pester you until you take it. They aren't anonymous. If you guys are curious, I think I can, let me see here. Where do I keep all that? School, Dearborn. So let's take a peek at like the winter semester. Yeah. So like this is what the eval looks like, what I get. And I don't get it actually until like grades are turned in anyway. But in case you were curious, here, it's anonymized. So, right, I had 7 out of 7 people take it. I was really impressed for the 2001 class last time. And I get different ratings, right, about the course, about me, yada, yada, yada. So the only thing that would make it not anonymous is if you go to one of these text boxes here and put your own name in. That's the only reason it wouldn't be. And I've only had one person do that. Actually, they didn't even put their name in, but they like put a very specific description of a very specific thing that happened to them and that they talked to me about in here, which I thought was very odd, but that's okay. Sorry, the highlighting is a little bit weird. Oof. But that's what it is. So please take a few minutes to fill that out at some point. The sooner you do it, the sooner Canvas stops pestering you about it. And these are included in my evaluation process. So my department chair does look at them at some point, I'm pretty sure. But you're also welcome to complain right to him if you have complaints. I apologize, I'm behind on the grading. It has been a really crappy November. Thankfully it's December, but I'm sick still, and this COVID thing is nasty. So it's been rough, but I appreciate you guys, and hopefully it's going well with you, and we can get there. All right, we'll talk a little bit more about recursion. We got some other examples. I really like to do this backtracking maze solver is super fun, or the 8 queens puzzle. But again, we'll do more of those next semester as well. When we get a little deeper into recursion, we'll have a whole recursion project we're going to do ourselves, which is fun. We'll talk about plotting. So I think the last thing we have then is to talk about your final project. Does that sound right? Let me come over to assignments and I'll get this thing loaded up for you here. All right. Final project. And let me make sure I put this in the right spot. And you guys are welcome to do this one in pairs if you want. Hey, welcome aboard, Alex. Glad to have you here. If you want to pair up, I want to this May. Let me know working with who, and please submit individually. So if you don't submit it individually, like if just one of the 2 partners submits it, it's really hard for me to grade both people. It's doable, but it's obnoxious to do in Canvas unless I make it a group project, which if I make it a group project, it gets obnoxious too. So I'd rather you just both submit because that makes life easy for me. So again, the goal is usually something a little bit bigger than this, but you know, given the circumstances, we're going to kind of tone down the expectations here. So we are going to build this is war card game simulator, and we're going to do a couple things with this. Right? Do you remember the card game War where you flip cards over and the higher card wins and takes the stack? While we're doing this, we're going to be checking. We're going to actually plot these results out here. Going to simulation with various numbers of cards and decks of cards. Let's see how many turns the game takes on average. So the idea is, if I just take a single deck of cards, all 52 cards, right, we get 2 up through ace. Ace, just assume ace is high, right? Ace is the highest card. So we have 2 through ace of each suit. 52 cards total per deck. So we're going to try saying, okay, let's just start with a single deck of cards and see. We'll just shuffle it up and deal them out to both people, and then we'll play the game of war and see how many turns it takes for a game to complete on average. And then we're going to try it with more cards. We can try it with 2 decks, with 3 decks, with 4 decks. You could try it with partial. So, maybe take half of a deck and just see, sample half of it randomly. So we want to do this sort of thing, and we want to see if the number of turns, what sort of relation it has to the number of cards that are in the deck. Is it going to be some linear relationship, or are we going to see a little bit more of a quadratic sort of curve here, as we're getting exponential more turns as we get more cards, and we're going to just see what happens, and we can plot our results, and I'll show you how to do all that plotting stuff next week as well. So the card game simulator, right, needs to play the cards. It needs 2 players, right? 2 players, which have a stack cards, and you win, add the cards to the bottom. So, I mean, it's called a stack, but it's not an actual stack data structure. Don't worry about that. Don't let the term throw you off there. Just add the cards to the bottom. If you want to use a list, that's perfectly fine. It might be a little slow, but that's okay. There's probably better ways to do this, but we can get to that next semester. So don't worry about it. Game is over. One player runs out. On a tie or war, have each player add 2 cards to the pile, and then check third. So, like, if you both turn over a 5, right? That's the tie, and then you say war. Flip 2 other cards. Just ignore those other 2, but then the third card both people flip is the one you're going to see who wins, and you win everything. Right? And there's some variations to this rule. I don't care too much. This might also be fun to vary if you want to compare that in your results and see if it makes any difference. But don't worry too much about that. If you don't have enough cards to do this, assume you just lose. Okay? That's probably the easiest, right? As soon as you run out of cards, you lose. So that'll just make life easier for you. But every time you win cards, right, you just add them to the bottom of your stack. You play cards off the top of the stack. We're going to see who wins. Okay, so we want to know how many turns it takes on average. So we need to be able to run this with different amounts of cards. So we probably want to do this in a nice object-oriented way where we have classes and they represent things. You don't have to, but, sure. I would rather you do it with classes, because that's sort of the goal here. We're still, an object-oriented design solution here. So we're going to use classes to do these things. I know it's not necessary, but it's going to make life a little easier than if we have this idea of more decks. It's easy, like I can have an entire deck of cards, and I'll run the simulator from like 1 deck of cards up through 10 deck of cards if we want, just for fun. You could really vary it any number you want, and you just run the game till it's done. Count that as the number, and we need to do this several times for each set to see like what an average is, and we're going to shuffle it up every time. So I might run the single deck maybe 100 times and see what the average is of 100. Then I'll run it with 2 decks and run it 100 times, run it with 3 decks 100 times, 4 decks 100 times, to try and get an average of each of those. Right, so like each starting deck size, run 100 times or so to get the average. Just to try and make sure we're not getting some skewed results there. Okay, so we're just doing a simulation. So it's not the mathematical proof or anything, which I'm sure some of our math folks, if they're still around, could show us how to do that sort of mathematical statistical proof, but we're just going to simulate it. And we're going to see, can we get close to a solution here? I think there's a term for that. But next semester we'll do some more card games, which are a lot of fun. We'll do poker and stuff, because I think poker is really interesting and has some fun stats. And yes, the stats are doable, but it's also easy enough to just simulate and do like a little Monte Carlo simulation. It's a lot of fun. And really, that's sort of what we do in this idea of data science, right? We're simulating stuff to try and get some results and see what we get. And it's not all the time. I mean, sometimes we can do the hard math and actually figure things out, but a lot of times we're building these simulations, we're building these models and saying, hey, this is what it looks like. Let's try a bunch of different things and let's tweak some parameters and see what kind of results we get in our simulations to see if we can get some data. And then we graph it, because people love graphs. Okay, so we're going to plot the results at the end. Okay, so I'll get a rubric set up for you guys a little bit later on this one here. We can go from there. But this one then is due, let's say the 22nd, 11:59 p.m. And I've got to have it by then because I got to get grades in like within 24 hours of you taking the quote final exam. But I think this was our final exam slot, and we can go from there. So it shouldn't be super complex, but definitely some steps to it to, simulating the game, how we track cards, how we track decks, put them all together, compare, add cards to the stacks or the lists, whatever we're doing, take cards off, put cards on, those sort of things. So definitely some work to it, for sure. We'll get to the plotting part later. I'll show you all that. The plotting is actually really easy and really cool in Python. You can do a lot of really cool stuff with plotting. But that's what I've got for you guys today. Let me know if you have any questions about the labs. I'm happy to help with those. Right, again, the lab is your practice. Usually we kind of meet in person, but we're not doing that, so it's kind of a bummer. But I can hang out and answer questions, whatever you guys have. Recursion Part 1. Don't forget to keep up with the zyBooks. I'll be running that on December 22nd. I think I've got that due date in Canvas for you. And we go from there. All right. If not, you guys have a great day. I'll hang out for a little bit, and I can hang out in Discord, answer any other questions you guys have. And we can go from there. So I know it's been a rough semester, but please reach out if you have questions, concerns, whatever. Happy to talk with you guys and work with you. Just let me know. I guess. Take care. No, I mean, there's a lot of math in programming, Angelic, but it's a lot of problem solving is more what programming is about. There's definitely some particular areas you might get into some heavy mathematics. It just kind of depends what you're doing. If you're working in data science, you're going to need a lot of math, a lot of stats for sure to understand what we're doing, crunching the numbers. But just kind of depends. There's lots of different programming. All right, cheers. Enjoy your coffee.